Okay, we're going to be starting shortly here, so I'll wait for a couple more minutes here until we have some more people show up. So thank you. Okay, we're going to start here. And what I wanted to do today is we are going to cover the heat reclaim topic today. So what I want to do is we do a series of classes regarding chillers. And most of the time we always end in heat reclaim. So there are some probably folks on this webinar who have not seen our previous emails of why heat reclaim is so important. So what I'm going to do is I'm going to show you my lead-in to how I did heat reclaim, and I'm going to look at a sample problem real quick, and then I'm going to start talking and discussing the heat reclaim. So in this case, we have a hospital project. We have a 400-ton chiller replacement. We have two existing 400-ton machines, R11. One is completely redundant, so basically they run one machine all the time, and they have year-round cooling requirements. And they plan to replace a second 400-ton machine later in the year. Okay, so in this case, we look at option one, and we have a centrifugal chiller, just a constant speed centrifugal chiller, a base ASHRAE efficient machine. And basically we're looking at 0.574 and 0.528. Most folks don't use constant speed machines because VFDs make a lot of sense, but that's not our topic today. Option two would be a centrifugal with a VFD, and that machine has a 0.574 full load and a 0.373 part load. Again, the difference between a centrifugal with a VFD is 0.528 part load versus 0.373 part load. And then we look at a high-efficiency tri-rotor screw, which again is a different presentation topic. It's our high-efficiency tri-rotor variable speed screw chiller, and this is 0.595 full load, 0.319 part load. When we do the quick energy analysis and we show the four different systems existing: high-efficiency screw, high-efficiency centrifugal with the VFD, and just standard centrifugal, we basically will have a, versus running that old existing machine, it's $76,000 a year to run the old machine, whereas a new machine, a 23XRV, will cost around $51,000 per year. So the obvious winner here is going to a high-efficiency screw chiller. And the lead into heat reclaim is this, okay? So I'm going to save this end user $25,000 a year by replacing his old machine with a new high-efficiency screw chiller. Oh, hold on a second. So again, how do we do better than this? And really is that we come up with option 4, which says, okay, we have a specific situation where we can do a 30XW 400-ton machine, 30XW 400-ton machine in heat reclaim. The building requires cooling almost year-round. We could deliver up to 140 degrees, 44, 56, 85, 3 GPM per ton on this one. And then is this really more efficient than the most efficient 23 XRV chiller, the most efficient 400-ton machine in the industry? Is this option more efficient than that, running it in heat reclaim? And the answer is yes. So when we look at the quick heat reclaim cost estimator we have, and I'll show you this later on here, we can show if we run this machine 4,000 hours of operating, delivering 120 degree water, and let's say our average load on the chiller is 60%, and we're unloading an existing 80% boiler plant, we can save that end user approximately $122,000 a year. Now that's assuming we have 10 cents a kilowatt hour, pricing of electricity is a little lower, and a buck of therm, and we know gas is a little lower right now. And we could play with that cost analysis, but look at saving $25,000 a year for a high-efficiency screw chiller versus the old machine, or putting in a heat reclaim 400-ton machine that can save them approximately $122,000, not by saving it versus the chiller, but by unloading the boiler plant. So what we need to do is we want to look at situations where we can unload the boiler plant and look at saving energy in reclaiming the heat from the chiller side of it. So again, the gold in the building is the heat. So that was my end of my presentation that I did last time, and I want to kind of go into the heat reclaim presentation now. Oops, there we go. So we're going to talk a little bit about heat reclaim. Why do we want to use heat recovery, heat reclaim theory, layout and sequence of operation, chiller configuration and selection, pony chiller versus like a redundant chiller. We'll talk a little bit about products and applications, and then we'll do an example job with energy analysis, and then we'll do an example project with a financial analysis. So why heat reclaim? Well, because ASHRAE tells us we need to do heat reclaim if your building operates 24 hours a day. And basically what it's equivalent to is a 1,000 bed, or if your service hot water exceeds 1 million BTUs, which is somewhere around 1,000 bed nursing home or a 75-room full service hotel. So we have to do the following: provide the smaller of 60% of the heat rejection load at design conditions, or preheat the peak service hot water draw to 85 degrees. And that one could get you into some trouble. So I want to kind of talk a little bit about that and where you can actually apply heat reclaim to a system and actually penalize your system by doing it. And you'll actually meet the requirements of this guideline, but it'll affect your chiller plant. So we're going to kind of discuss that a little bit. So let's look at an example building. Chicago full-service hotel. Building operates 24/7, 7 days a week, 24 hours, 7 days a week. We have 4,074 hours of simultaneous heating and cooling hours. So cooling is the AC and the heating with domestic water. And we've run hours in bin analysis with airside economizer. And what we have is 1,718,000 BTUs of chiller heat rejection available for water heating in those hours. So that's approximately a 100-ton chiller that we're going to use for the rejection. So what does it cost to heat that water, that 1,718,000 BTUs per hour for 4,000 hours? What does it actually cost by using other methods of doing it? So let's look at electric resistance hot water heaters. It's going to cost approximately around $246,000 a year for that hotel to heat that much water for the hotel. 80% efficient gas hot water heaters, it's going to cost approximately $87,000 per year. And then 94% efficient hot water heaters, it's going to cost approximately around $74,000 per year. heat reclaim point of use, which means that we're just going to temper the hot water, temper the makeup water. That will say that'll cost them about $56,000 a year. I'm sorry, the point of use utilizing the whole heat reclaim of the machine is going to cost them $56,000 a year to reheat the water with the chiller. It's going to cost them $56,000 a year, or what we call heat reclaim preheat, which is what we're going to do is preheat the makeup water on the system, which would cost them about $7,600 per year to do that. So really what we're looking at is we're looking at the analysis of heat reclaim, the point of use, $56,000 a year to do it, versus high efficiency boilers, which you think you're doing the best thing possible for the building. You're doing 94% efficient hot gas, hot water heaters, and it's going to cost them $74,000 a year to do that, where it's going to cost $56,000 with the chiller side of it. Okay, so let's look at the heat reclaim process. So we have our heat in on the evaporator, we have our heat out on the condenser, and then our work in through the compressor is the electricity required for the work in. When we look at a traditional parallel chiller plant, again, we have high efficiency variable speed chillers. We're using condenser water relief with low condenser water temperature, reduced lift. Primary, secondary system, and the heat is wasted out of the cooling tower in this configuration. So when we look at this next slide here, again, we have multiple chillers. And with this scenario here, if you look at what's happening on the condenser side, we have our service water coming out, and we have it coming in, and we have it leaving at 85 degrees. Now, we're meeting the intent of ASHRAE by preheating our makeup water to 85 degrees. However, what are we doing to do this? So how are we actually going to do this? Well, we're doing this by actually artificially, we're going to raise our condenser water temperature in order to get that 85 degrees. So that does not allow me to do any relief on the condenser side based on ambient outdoor air temperatures. And as people who have listened to me and discussed our last chill water projects, what our whole intent is to reduce lift on a chiller plant, so therefore operate chillers with cold condenser water. And in this case, I'm meeting the intent of ASHRAE, but I'm not able to run my machines with cold condenser water, because if I run them with cold condenser water, I cannot provide 85 degree minimum out of that heat exchanger. So I hope that explains that enough. Higher leaving condenser water temperature increases and basically reduces the efficiency of the chiller itself. If you look at it from a pressure enthalpy standpoint, we show that basically as we go from point A and B on the sheet here, and we go to B, L, and AL, what we're doing is we're using higher condenser water temperatures, and what we're doing also is we're increasing the lift on the system. That point B to A, that is the work that we have to basically do in the system from the chiller standpoint. It's the lift. It's the saturated condensing. We have a saturated condensing temperature minus the saturated suction temperature. That is our lift. As I increase lift, the chiller plant gets less efficient. As I decrease lift, it gets more efficient, and it saves the customer energy when I decrease lift. So I don't want to necessarily increase the lift on the chiller plant in order to meet my ASHRAE requirement for heat reclaim and get my 85 degrees. There's better ways of obviously doing this, is what really I'm getting to. So when we look at a chiller, and we have a typical chiller where we look at the load line on it, and this is basically a full load chiller plant. So at cold condenser water temperatures at 67, 65, 60, 75, we're running it at 0.37 kW per ton. At 100% load at 75, 85, we're at 0.48. As we raise that up, and we'd have to raise that up in order to get that 85 degree water, we're basically taking a huge penalty hit on the chiller plant in order to do this. So again, there is a better way to do this. What is the penalty, the true penalty to do it? Well, if we look at that same 800-ton chiller plant that we just looked at, and we raise the condenser water temperature to handle the heat reclaim, so that means the chiller energy cost for 4,074 hours is over $177,000 to basically artificially increase the chiller plant, the leaving condenser water temperature, to meet the heat reclaim requirements. So compare that to running natural gas hot water heaters at $75,000, and therefore you would never expect an owner to spend $177,000 just to save 75K. There's obviously a better way. So in this case, the math doesn't add up. It's not a good situation, and that's why we're talking there's a better way to do heat reclaim. So what we typically like to see is we would like to see, here's a couple of different scenarios we're going to go through here. We have a heat reclaim multiple chiller plant, and what we're going to do is we're going to put a heat reclaim chiller in parallel with this load. So we have a 30HX or XW heat recovery chiller. It's piped in the chiller plant in parallel, sized to match the heating load, and we're going to control it to a cooling set point in this application. So whatever heat I get out of the condenser side, I'm going to use that for my hot water load, but I'm going to control to a chill water temperature because it's in parallel with the others. And what we're trying to do on that case is we're trying to control to a common leaving water temperature set point. Now, that's one way of looking at it. Here's another situation with heat reclaim in the preheat, where we're basically preheating water, domestic water. So we have a 30XW XHXC, 30XHXC, and I'm sorry, I can't see the, hold on a second. So I have a 30HXC 206. I have chill water return of 52, and I have a chill water supply of 40. And what I'm doing is I'm serving this, hold on a second. I'm serving this this condenser, the city makeup water, which I have 50 degrees entering, and I'm basically leaving at 90 degrees. Okay, so on this side I have the city water. I have a 127 GPM of city water, and I have a 30 HXC 206. And you'll notice that the flow of this machine on the condenser side is not going to match the flow of the city water, domestic water requirements. So what we're going to do is we have a 30 HXC. We're going to put a little condenser water pump with a VFD on it. It's going to be controlled by the chiller, this domestic water pump. We're going to put a little storage tank in there because we like mass in our system, okay? And we have a double vented heat exchanger here. So what we're going to see here is we're going to be able to do this. This is for heating domestic water. We can also use this situation for heating pool hot water heating requirements. Heating a pool is a huge requirement when you look at facilities. I've seen some cases where they're spending $40,000 a year to heat pools. I just ran into a situation the other day for a residence where they were spending $17,000 a year to heat their pool each year. Okay, and this was an outdoor pool just in our backyard here in St. Charles. So we know that it costs a lot to do this. So what we're going to do is we're going to try to capture the heat off of the machine to preheat the water and not use, obviously, natural gas or other means to heat the water. So if we look at this case when we're doing domestic water, there's a typical relationship between the condenser water. So the last machine, which is a 30HXC 206, we had a condenser water GPM of 513 GPM, which is a 10-degree delta T. And on the hot water side, we had 127 GPM with a 40-degree delta T. So that's what our heat exchanger is going to do. And you can see this little selection if you could read it. It's an alpha Laval selection. And in this case, it's just a slightly different selection where we show our relationship again between the condenser water. Excuse me for a second. Sorry. So we could see our relationship between our GPM on the condenser side of 137 to the GPM on the domestic water side of 27. And there's typically a relationship of a 4 to 5 to 1 relationship on condenser to domestic water side requirements, because typically you have less demand for the condenser. You have less GPM required for domestic water. Let's look at another application where we have a heat reclaim chiller in parallel. But in this case, what I want to do is I want to control the chiller, and I want to have that chiller controlled to a hot water temperature set point. Okay, again, it's still piped in parallel with my other chiller plant, but in this case, I want to have the machine controlled to a hot water set point. So how are we going to do this? Well, what we're going to do is we're going to put a pump here. We're going to have a VFD, and this VFD is going to be controlled by a temperature set point in the leaving water temperature set point. So we're going to control this heat reclaim chiller. We're going to provide whatever heat required for this hot water load. It's going to be controlling to that hot water load. And then whatever chill water temperature we deliver out of the machine, we're going to control that temperature by slowing down the flow to that through the evaporator. So we're going to slow down the flow with the VFD on the pump. So if my set point rises, I'm going to reduce the flow of that through the chiller, and then I'm going to maintain set point of, say, 44, 42 degrees. Here's another way we could look at. We're going to basically do something called like a pony chiller, where we have it piped in the return chill water line, and what it's going to do is it's going to unload our existing chill water plant. Again, it's going to be sized to match the heating load. It's going to be controlled based on heating load, and all it's going to do at that point is going to be your first on and last off chiller. And this will basically, so whatever cooling I get out of it, it just unloads my cooling plant. And again, I can now do proper condenser water to leave on my cooling tower. So when I have cold days out and I have cooling requirements, first of all, if my heat reclaim chiller cannot handle the complete load, at that point I will turn on the other chillers in order to handle the load. And the machines are going to have something we called low source protection. So I can control to a hot water temperature. And what they do is, so they're going to control to a hot water temperature set point, and then they have something called low source protection, which will prevent it from overcooling by reducing compressor stages if necessary. As I reach a certain suction temperature, it'll unload stages, but it'll also be trying to control to a hot water set point. If at a certain time I cannot meet that hot water set point, I will just raise that. I will basically unload a couple stages on the machine and keep the machine operating and running in a stable, not always cycling on and off environment. Here is another situation again where we have a hot water where we have a 30X HXW, HXC, and we have it piped in the return line. And for anybody who's seen our presentation on series counterflow 23XRVs, here we have a chiller plant, which is the 23XRV, which is from my previous presentations. You could see it is the most efficient two or four or multiple chiller plant in the industry in this size range in series counterflow. And then what we're doing is we're going to further basically make it that much more efficient by putting a heat reclaim chiller in this chiller, and it's going to be controlling to a hot water set point, and it can either dump water to the cooling tower or the hot water source based on whatever is needed on the hot water standpoint. And it also can be used as a redundant chiller. So you could have basically an N+1 design, have a series counterflow chiller, and use your heat recovery chiller as your N+1 chiller in this situation. Both chillers, all the chillers are 400 tons. The heat reclaim chiller controlled a hot water temperature. It can also dump its heat to the cooling tower if necessary. So this right here, this chiller plant, the 23XRVs with the heat reclaim, I feel is the most efficient option from a chiller plant standpoint of unloading both the chiller plant and also unloading the boiler plant. So a couple of application guidelines. We can use it for potable water. Again, if we use it for potable water, we need a double wall vented desuperheater or a double wall vented heat exchanger. The difference between desuperheater and a full condensing is a desuperheater, I will only be able to capture about 25% of the useful heat. What it does is it basically takes all the heat required before it hits the hits the mixed phase. It basically takes it to the mixed phase point. So that desuperheater will only be useful for about 25% of the heat. But we do use it, and we do see those applications. We can look at VAV reheat applications where they need space heating in the summer, and we can utilize, let's say like a desuperheater or a full condensing heat reclaim chiller, and we have a properly sized storage tank, and then we basically use that heat to use for VAV with reheat. Pool heating is an absolutely fantastic application, and we have to make sure we have a rated heat exchanger in that case. And then the temperature options, we have a high temperature, hot water, point of use, or we can preheat it also. Sizing options, we have a redundant chiller to match those in the chiller plant. So that was the one we just discussed previously. We can look at something called a chiller that matches the heat load, or a pony chiller. So that pony chiller would be strictly sized for what your simultaneous heating and cooling requirements are. So again, the key piece on heat reclaim is I need to have a chiller plant that basically has multiple simultaneous heating and cooling hours. Okay, I need multiple heating and cooling operation of heating and cooling in order to make it properly work. So that in this case, the pony chiller would be sized to handle that. Okay. Again, think first on, last off. Here's a little heat reclaim example, just a quick sizing example, just kind of shows you just a real quick one, and then we'll go into further the products here. We have a K-12 school, Southeast U.S., no gas service, so we have approximately 450 tons of chiller. We're using two 30HXE 246 water-cooled screw chillers. We have a chill water temperature of 45, 55, and then the condenser side 85, 95. We have a domestic hot water requirement, which is 126 kW of electric heating requirements. And if you remember back to when I first showed you the slide of how much it cost to heat water, right? So if you looked at that one typical slide, it was about a 4-to-1 relationship between heating with a heat reclaim chiller versus heating with an electric heat domestic water. So again, we're going to size the heat reclaim chiller at 30 tons, which matches the 126 kW of heat for the domestic water. 30 tons in a 450-ton chiller plant. It's a pony chiller. We're going to use it first on, last off, whenever there's domestic load requirements. So the heat reclaim chiller, 126 kW electric heat rejection at a cost of X to run, or do we run 126 kW of electric heat at the cost of 4.37 times X, which is that relationship between running my heat reclaim chiller or running an electric domestic water system. And there is surprisingly a lot of electric hot water heaters, domestic water heaters in Chicago. And there's a lot of times when you find that they're running both of those simultaneously. You find a lot in hotels where they have a existing swimming pool, where they're running the pool heater, and they're also running their chillers at the same time. So there's a lot of applications here, and I don't think we've quite captured it and grasped this as a whole engineering culture here. We haven't done a lot of heat reclaim. We've started to grow. It started to grow, but we haven't done enough of them yet. So let's look at heat recovery focus again here. We have, what does it cost to do simultaneous heating and cooling? So electric hot water heater, boiler, when I convert it, it costs 3.5 kW per ton to run that domestic hot water heater boiler. Okay, my chiller, it's going to cost about 0.6 kW. Okay, versus a total kW of 4.11 kW per ton on the system. So a heat reclaim chiller can deliver 44-degree water while heating hot water to 140 degrees, and that is 1.48 kW per ton. So do I want to spend 4.11 kW per ton or 1.48 kW per ton? That's where the real savings is. So let's look at gas. So let's convert the gas. The biggest energy hog in a chiller in a building is basically the boiler plant. Okay, so you could look at replacing or unloading high efficiency boilers. So let's look at some gas boilers running at 0.4. They're basically 4.4 kW per ton. We have a chiller that removes heat at 6.6 kW per ton, or 5 kW per ton total. Again, 5 kW per ton or 1.48 kW per ton. I understand, and also in certain parts of the of where you're located, they have different electrical rates and they have different gas rates. So there may be certain paybacks, and that's why we have a nice tool to do the quick payback analysis for us and just make sure that the project actually will work and it makes sense. And we can do a quick snapshot, and I'll go through that tool here real soon. So what we want to do on a domestic water system or any other, what we want to do is we want to look at the domestic water requirements in the facility. And we could size the heat reclaim chiller in a couple ways. We could size it so it's always going to handle and it's always going to run on this low part right here. Or what we can do is we can size a slightly larger heat reclaim chiller with a preheat storage tank, which I think is a better way to do it. And size allows a storage tank, so we're not cycling on and off chiller. We're basically charging a storage tank, and that storage tank is basically then serving the heating load. Here's an example potable storage water system that we have, where we basically have a water heater, we have a preheat storage, we have a Carrier 30 HXA chiller with a heat reclaim bundle here, and we're basically reclaiming. We have a heat reclaim supply feeding the water heater. Here's just a little piping scenario of how we can actually pipe this on a domestic water side system. Okay. And in our double wall vented desuperheater is right here. So it's the double wall vented desuperheater, which takes hot refrigerant from the machine, basically passes it through the double wall vented desuperheater, and then now we have potable water that we can deliver to our hot water system. So this is just for reference if you want to figure out how to pipe your system. So when we look at an example here, we always think of economizers always reduce energy, right? So if I turn on economizers, that means I unload my chiller. If my chiller is running at say 0.6 kW per ton, and why would I not maybe possibly looking at starting running my heat reclaim chillers longer, maybe changing my economizer set point to maybe 50 degrees versus 55 degrees and running my heat reclaim chiller slightly longer. Because why not start the heat reclaim chiller and use less economizer and unload a hot water boiler plant at 3.5 or 4.4 versus saving the 0.6 kW per ton. So it's just a couple of things you want to look at when we're looking at a building. It may make sense to change your economizer set point if you have a heat reclaim application. So let's look at the products we offer. We have a 30 HXC. This has basically been the workhorse in our market. It was the first machine out with 134A, fits through a door. Standard, it produces 114 degree water, and with a compressor modification, it can deliver 120 degree water. It's from 65 to 265 tons. Potable or potable water available with an external heat exchanger. We have what we call a 30 HXA chiller. This will allow us to produce hot water up to 135 degrees, water or air-cooled. So we could put a remote air-cooled condenser. We could put a little desuperheater on this. We could do full, partial recovery. It comes in the capacity of 65 to 265 tons. Again, potable water, you can use the double-walled vented desuperheater to provide it, or an external heat exchanger if you need it for potable water. And then we have what we call it's Carrier's heat machine. It's the 30XW. It was designed as a dual circuit machine from 150 to 400 tons, but right out of the box you could produce 140 degree water with a condenser box cover change. The standard unit will produce 118 degrees, but we can do hot water up to 140 degrees. It'll provide full condensing, and we can do potable water with an external heat exchanger if you require it. This is what a product that I think is pretty cool, and that is we have a 30 RB chiller. And what we have is it's an air-cooled machine. It goes from 60 to 190 tons. And a lot of times what you have is you have hospitals or different air applications where they want to put a little air-cooled chiller to run in the off-season because they have a chiller demand. Well, typically if they have a chiller demand in the off-season, they probably have a boiler demand in the off-season. So in this case, we have a heat reclaim bundle built into the machine. And it has all the controls built into here. We can provide hot water up to 131 degrees, dual circuits, and it'll either say, okay, I'm in heating mode. It'll reject all the heat over to the heat exchanger, and then it'll go into heat reclaim mode and control the hot water temperature. When that's done, it'll then reject all the heat through the normal conventional means, which will be through the condenser fans outside. So all the controls built into it. Fantastic product for heat reclaim, 60 to 190 tons right out of the box. We also have on the smaller scale, if you want to do some water-to-water heat pumps from 1 to 30 tons, we can do that also. From a heat pump standpoint, we can do some heat reclaim also. 30 MP, we have what our 30 MP, it's basically from 15 to 45 tons. Right out of the box, it'll do 140-degree water. It'll provide for heat reclaim options. We have a 30 MPW, which is a water-cooled, and then we have a condenserless option, which is a 30 MPA. In the condenserless option, you could do such things as like a de-superheater, and again, you have for potable water use, you'd have a de-superheater with a 30 MPA or an external heat exchanger in the system itself. So those are our products. Now let's look at a couple examples, economic examples on the system, and then we'll go into questions if anybody has any questions. Let me just check here and see if anybody has any. I think we're all set here right now. So let's look at an example. We have a multiple chiller plant, year-round cooling load, predictable domestic hot water use for a hotel. Chiller provides 4454 chill water as a byproduct of domestic water heating. So run hours are maximized and many uses for hot water. So if you look at our selection here, we have a 30 HXA machine, okay, and we have on the tons, it's 101.6 tons. Our heat in on the equation is 357 kW. And the work in, which is the electricity required for the compressors, is 172.1 kW. And on the condenser side, since we're going to recover all the hot water we possibly can from this for the domestic hot water heaters, we can get about 503.7 kW of hot water output for heat rejection for requirements. So let's look at this. So our COP of heating, and I'm going to take all the questions at the end here, so I know we've got a couple questions that popped up, and I will answer those questions here at the end. COP of heating, work out divided by heat out divided by work in. On the COP of heating, I'm at 2.993. The COP of cooling, again, I have my heat in 354, my work in 172. I have a COP of 2.1. When I look at the total COP, I'm basically adding them up, so I have a total COP of about 5. If all the heat is captured and used to offset boilers or hot water systems for the simultaneous heating and cooling requirements, we will have a COP of 5. When we look at the heating options here, we have a COP of heat from heat reclaim, which is 2.93. COP of a natural gas hot water boiler, hot water heater is 0.94 on a condensing or 0.8 on a non-condensing. COP of an electric water heater is 1, but what about the generation and the transmission efficiencies of the existing lines? Or do we want to look at running a COP with a heat reclaim chiller of 5? So now you could really see where we can, if we can somehow unload that boiler plant, we could really make this building extremely efficient on the hot water side, and then also by not penalizing the chiller plant. So what we want to do, we want to run a chiller load. We look at the domestic hot water use profile, and we're using our Carrier HAP building analysis program to do a simulated energy analysis on this situation. So from our annual energy cost standpoint, this is what we get. So we look at a conventional hotel using electric domestic hot water heaters. So we have our air fan system, which is $49,000 a year. We have our cooling requirements, which is $21,000 per year. That's by running the chillers. Pumps, $6,786. We have cooling tower fans of $9,383. HVAC subtotal of $87,819. And then, but down here we look at the domestic hot water heater for electric. It costs $280,000 per year to run those hot water heaters. So a grand total of $524,000 per year. Now let's look at the natural gas point. Again, same cooling, same air system, same cooling, same pumps, same cooling tower. The only difference is now I'm not doing it with electric, I'm now doing it with natural gas, and now the total is $357,000 per year savings. So it makes sense to go to gas heat on most applications. Now let's look at the hotel with heat reclaim. Again, the fan system doesn't change. However, my chiller plant does change. The cooling plant goes from $21,000 per year, and it costs money to run chillers at with hot water. Okay, it costs $38,000 per year to do it. Okay, now I save in some pumps from the cooling tower standpoint, and I have no cooling tower energy. Now they're showing that basically in this application we're utilizing all the heat from this situation, and we're not having any cooling towers at all. That may not be the case in some situations, but you could see the dollar difference here down here, where we're looking at $247,000 subtotal. So even if I add some cooling tower operation cost, I'm saving, let's say, around $100,000 a year versus this conventional domestic hot water heater with running a hotel with heat reclaim and basically unloading the domestic water heaters in this application. So let's look at it and say, when is the best time to do a project for heat reclaim? Obviously when it's new construction, and then when they're purchasing new chillers. Most of the time when you put in a new chiller plant, there's very few applications that I've seen where they're just they have an existing chiller that's say 15 to 10 years old, and I want to put a new high efficiency chiller, and I want to make sure there's a 3 to 5 year payback on the system. And in most cases, it's very rare for that to happen. I haven't seen, unless there's a huge maintenance cost involved in that chiller. In that case, you'd probably be buying a new chiller anyways. So when are you going to add a chiller in capacity? Or we want to look at the other way, is when added chiller capacity is required, necessitating a chiller addition, either adding a new chiller. So we want to look at a couple different ways when the best time is to do a heat reclaim chiller. So we're going to perform a cash flow analysis for either the total project cost or the incremental cost of configuring the equipment for heat reclaim. So we're going to do a little economic analysis. We're going to use this from Jones Lang LaSalle, which basically shows this is just a standpoint of how we're going to do the analysis. We're going to use a cost of $1,000 per ton for replacement costs by adding a chiller, and that's how we're going to do this in this analysis. So we have a 500-ton. The owner wants an extra 100 tons of capacity. So we have an existing 400-ton chiller plant. We have a multiple two 400-ton chiller plant. He wants to take one 400-ton machine, and he wants to replace it with a 500-ton machine because we need an extra 100 tons. So we're using the 1,000-ton replacement cost. We only have 2,500 hours of operation on this chiller because we have 2 chillers in the plant. We're using a 10% discount rate. The new part load value of the new chiller is 0.444. The old part load of the old chiller is 0.705. In this case, we're showing 12 cents a kilowatt hour, and as long as we're using the same baseline, this is what we're using in this case. So the chiller replacement cost $500,000. We're using 500 times 1,000, so $500,000 for chiller replacement cost. We're saving in energy $31,320 per year in energy over the old system. And when we look at the payback, again, where I mentioned before, we very rarely are going to find a payback by just replacing a chiller with a more efficient chiller. And in this case, when you do the net present value, we show a simple payback of 15.96 years. So in general, a conventional chiller replacement does not pay for itself through chiller-only efficiency gains. So let's look at that same last question we did where the owner wanted an additional 100 tons. Let's look at basically giving him a 100-ton heat reclaim chiller for addition, and let's utilize basically the energy by unloading his boiler plant in this case. So we're going to use, again, the 1,000-ton chiller ton per replacement cost, 10% discount rate, 4,500 hours per year of operation. Well, that's because we have simultaneous heating and cooling in this plant where they're running 100 tons simultaneously, and they're also running boilers or domestic hot water heaters. So again, we're going to maximize the operation, first on, last off. So let's look at the energy analysis and the economic analysis on this. So we have a chiller replacement of, we have 100 tons, so the chiller replacement is $100,000. We have to add a heat exchanger, which is $24,000. Okay, so that comes to a cumulative cash flow of $124,000 for the chiller replacement on that 100-ton machine. So we have a decrease in pump electrical energy because of the cooling tower, and the cooling tower fan decrease. However, we are going to increase the energy of the chiller plant by $8,400 per year. So it's going to cost us $8,400 per year. However, we're going to save $58,000 in natural gas savings in this particular application. So we save approximately $56,700 per year by running this heat reclaim chiller in this application. And we show a net present value of $359,000 and a simple payback of 2.2 years. That's using basically a 100-ton machine with a 1,000-ton chiller plant and 4,500 run hours. So it's all how you look at the application, and maybe in some cases it doesn't make sense to replace the chiller. Maybe it makes sense to add a heat reclaim chiller for extra capacity. So it's just outside the box looking in. So that is all I have for today. So what I want to do here real quick is I want to show you the estimator, the heat reclaim estimator that I have, and it is right here. So it's very simple to use, and the reason why I like this is because it's a very simple, oops, and for some reason it is not, my macros are not enabled because I just switched computers, and I'll just show you how this thing works, and you'll see at the bottom here. But in some applications it may not always work. So in this case, you plug in 0.1 kW per hour, and you could put whatever your electrical rate is. You put in your demand charge if you have it. You put in your cost for natural gas, and then it basically will do the conversion. We look at the number of hours of simultaneous heating and cooling. And in this case, we are looking at a little 30-ton water-cooled unit. We have 3,000 hours of operation. We're using 120-degree water. Our average load of the chiller is 50%. And we're unloading a boiler plant that's 90% efficient. And what we're showing is we're going to save that end user approximately $4,400 per year by adding just a little 30-ton heat reclaim chiller in his plant. Okay, so it may not always work here. Let me just see if I could find this. See if I could find a slide that actually works here. My macros for some reason are not enabled, so I apologize about that. But either way, I have this quick, easy estimator to look at if the project is viable or not. So if you may want to look at it and just do a quick snapshot, and I'll be happy to send over this spreadsheet to you. So if you want, and if you are interested in it, please send an email copy to myself or Ryan Hoger. Again, my name is Mike Smid with TEC. My email is mike.smid, S-M-I-D, at TECmungo.com. So any questions? Let me look at the questions here real quick and see what we have. Hold on a second. How does it cost compare against domestic? Okay, I think how does first cost compare against conventional domestic hot water systems? Dan, in this application, we have to look at what it costs to add the option in the traditional. And some of our chillers, the heat reclaim option comes standard with it. So I wouldn't say that we ever want to replace domestic water heaters. So those domestic water heaters are always going to have to be purchased, because you're always going to need that backup in there in case the chiller is for some reason not running. So a traditional cost to add heat reclaim to a chiller, it's typically by chiller basis. I would say on a air-cooled machine, that oftentimes it's somewhere around, I don't even want to guess here at this point and steer you down the wrong direction. So it depends on if you're going to do a desuperheater, you're going to do full condensing, you're going to use the air package air-cooled chiller, you're going to use a chiller that already has the heat reclaim option, so therefore it doesn't cost you anything to do it. So there's a bunch of different ways we can do it. So any other questions, please let me know. Let's see here, I got some. Okay, I think that's it. If anybody has any other questions, please send me an email. We will. My cell phone number, if anybody would like to discuss an application, is 847-630-7867. 847-630-7867. Thank you very much. Take care.